Okay, so welcome to the last session of today. It's the best paper and best student paper session. And our first speaker is Aviad Rubinstein, telling us about settling the complexity of computing approximate two-player Nash equilibria.
Thanks, Irit. So in 1951, Nash proved that every single game has an equilibrium. Let me just remind you that we'll talk about Alice and Bob, but equilibria are very important, not just in game theory. They're used for markets, to model traffic jams. They're used by biologists. Anyway, once in equilibrium, every players don't want to deviate. But the million-dollar question is, how do they get to this equilibrium? This question has been studied for over 100 years by economists, in the last few decades also by us computer scientists. This is just a tiny sample of the works on this question. And the remaining open technical question in this line of work is there a p-task for a two-player Nash equilibrium? So I'll spend the first half of the talk telling you about some algorithms that get close to a p-task. And first of all, you'll see there's so much work that will convince you this is the most important problem. Second, they suggested the p-task was just around the corner, and I did hear from people in the community they're sure we're getting there. And for people like me who do harness, algorithms are just obstacles for harness, or pessimism for the pessimists. Okay. So first, the algorithm is the Lemke-Hausen algorithm. It finds an exact Nash equilibrium in two-player games. N by n means each player has an n by n matrix with their utilities. It runs in exponential time. But it implies that Nash is no harder than the following problem, which is called n of a line. N of a line, you have an exponential sized graph that is given implicitly by circuits that tell you what are the neighbors of each vertex. And you have an odd degree vertex 0 at the beginning. You're giving an odd degree vertex. There must exist another odd degree vertex, and you want to find another odd degree vertex. So n of a line is probably not NP hard because there always exists a solution. But we don't have any algorithms that run any better than the exponential time trivial algorithm. And the class PPAD, defined in 94, is the class of all problems that are reducible to n of a line. And Daskalakis, Goldberg, Papadimitriou, and Chen Teng proved that computing a Nash equilibrium is indeed PPAD complete. So it's as hard as this n of a line problem. Furthermore, even a 1 over n approximation, here the approximation is additive, so smaller means hard is a better approximation. Even 1 over n approximation is still PPAD hard. The main question is, what about epsilon approximation for constant epsilon? LMM algorithm finds an epsilon equilibrium and runs in quasi-polynomial time, so n to the log n. And it means that Nash is probably not going to be PPAD hard because we have a much faster than exponential time algorithm. Well, we believe n of a line takes exponential time. And we want to ask, is this quasi-polynomial time actually necessary? There are many other problems with very similar algorithm that run in quasi-polynomial time. For example, you can decide decision versions of Nash. For example, if you want to find the best epsilon Nash equilibrium, that's also quasi-polynomial time. A bunch of other problems like densest K subgraph, and all run in quasi-polynomial time. All of those we can ask, do we actually need quasi-polynomial time? So the exponential time hypothesis, we hypothesize that 3-sat actually takes 2 to the omega n. Notice this is weaker than the Seth, the strong ATH. This is much weaker, just 2 to the omega n. And there is this technique called birth repetition that gives us reduction of size 2 to the root n. Is this point somewhere? I'll give up on the pointing. So capital N is 2 to the root n, and then by ETH, the running time is capital N to log capital N. And we can use this technique to get quasi-polynomial lower bounds for all of these problems. So if we're going to talk about Nash, there is no way we cannot expect to use the ETH for 3-set, again, because there always exists an equilibrium, but we can assume ETH for p-pad, which means that this n of a line problem actually takes 2 to the n time, to the omega n time. The other problem that we have, the other obstacle that we have is all those other reductions use the PCP theorem. And we don't have a good analog of the PCP theorem for PPAD. So I promised to tell you about algorithms. So here there is a series of improving approximation algorithms. The best thing we know is delta is approximately 0.33. And we don't know can you take delta to 0? Again, that was open. And there are a bunch of special cases for which we can get polynomial time algorithms. But the general case, we didn't know. And finally, the main theorem is that if you are willing to assume this ETH for p-pad, then approximating Nash in a 2-player game actually takes quasi-polynomial time. Let me just comment that the proof uses PCP-like techniques. This is the first time in p-pad that anything, even error-correcting codes, are used. And I also want to comment that there is a conjecture of what would be a PCP for PPAD, and this conjecture is still open, despite the fact that we have PCP-like techniques here. Okay, let me tell you a little bit about the proof. So the framework of how we prove hardness for Nash in general is we start with this n of a line problem, and then we reduce it to the problem of finding a fixed point that is guaranteed to exist by Brouwer's fixed point theorem. So we have, I can actually run over here. We have the continuous unit hypercube, and we have a function from the hypercube to the hypercube, and we're trying to find x such that f of x equals x. And we show this is as hard as n of a line. Then we reduce it to the problem of finding an equilibrium in an n-player game, and eventually from n-player we can go to 2-player. So this is the general framework. It was first used by Daskalakis, Goldberg, Papadimitriou, but they use a 3-dimensional cube. If you're using a 3-dimensional cube, you cannot hope to get so you want a hardness of approximation, so you cannot get hope to get approximation stronger than exponential, because in finite dimensional cube you can get a grid. 1 over n grid. So they get an exponential 2 to the minus n hardness for Nash equilibrium. Chen Deng Teng use an n-dimensional hypercube, and that allows them to go up to 1 over n hardness. And recently, last year, we showed how to take an old construction of Hirsch, Papadimitriou, Vavasis from the 80s and actually get epsilon hardness for this finding approximate fixed point. This gave us, Ron, is that a question? Oh, okay, sorry. So this allowed us to get epsilon hardness for computing an equilibrium in an n-player game. But when you go from n-player game to 2-player game, each of Alice and Bob gets approximately half of the players. So epsilon, if one of the players is epsilon deviating, we lose a factor of n, and you only get epsilon over n hardness for 2-player Nash. So this is a good point in the talk to define what I mean by epsilon Nash equilibrium. So Nash equilibrium, hopefully all of you know, but it means that given what everyone else is playing, my mixed strategy is the best response to what everyone else is playing. My distribution over strategies is best response to what everyone else is doing. Epsilon approximate Nash equilibrium means that what I'm doing is epsilon optimal is within additive epsilon of the optimal thing given what everyone else is doing. And this has to hold for every player in an n-player game. And interesting relaxation of this that we introduced last year, or actually this last ITCS, is this epsilon delta weak Nash, which means I'm simply requiring that 1 minus delta fraction of the players play epsilon optimally. The other delta fraction of the players can play arbitrarily. So this is closer to what we're used to seeing in a hardness of approximation. It's also a natural relaxation. So if there's a tiny delta fraction of the population that does something silly, I should see that. Okay. If there's a tiny fraction of the population that does something silly, we are not going to worry about this. So, or the catchphrase is, can almost everyone be almost happy? Okay, so in last ITCS, we assumed this PCP conjecture for PPED, and that gave us a harness of this, an n player of this epsilon delta weak Nash. And now delta of the players are epsilon deviating, so we can use this technique Berth repetition, which I didn't tell you much about, but we can use it to get epsilon times delta harness for 2-player Nash, which would be awesome, except we don't know how to prove this PCP for PPED. So here's what we actually do. We use this old technique of Hirschman-Massis, and we add to it some error correcting code, and we get harness of so. Earlier, we had a harness in infinity norm, and it turns out the right thing to do is look at a finite norm. So specifically, we get harness in 2 norm. So now a constant fraction of the coordinates are a constant far from being fixed point. Now, you'd think this would get us immediately to epsilon delta Nash. Not quite. There are a bunch of PCPs. Something amazing happens when you have a PCP with root n queries. And we can get a harness for this problem. So root n queries, if you use the optimal randomness, optimal pseudo-randomness, you only need approximately root n questions. And for each question, we construct a player. And each player has, if you're being queried about root n bits of your proof, then you have 2 to the root n possible answers. So each player is going to have 2 to the root n actions. So this is the sub-exponential blow-up, and that means a reduction in sub-exponential, so we get a quasi-polynomial harness for 2-player Nash in epsilon delta. And up to a lot of omitted details, this is the entire proof. Okay, so a lot of people have been asking me in this conference, you settle the complexity of approximate Nash equilibrium, what's next? So I think this is, first of all, there is still this PCP for PPED that I would love to see resolved. But as far as exact Nash equilibrium, we have all these hardness results that essentially exactly characterize the complexity of computing Nash equilibrium. If you try to, what happens when you try to convince game theorists that Nash is hard? Well, we have all those assumptions, PPD not equal to P, ETH for PPAD, or even NP not equal to P, or P not equal to P space, whatever. Those assumptions are inaccessible to people outside our community. So of course, I don't expect any game theorist to read the proof, but even the theorem statement as it is not accessible. So as far as I think that what game theorists can see from this is computer scientists think that computer scientists prove that computer scientists think that Nash is hard. And this is a problem with computational complexity. We don't know anything better than proving conditional lower bounds. So what we can do is we can talk about communication complexity, and this is a very simple model. Alice knows her own payoffs. Bob knows his own payoffs. And the question is just how much do they have to communicate to compute this approximate Nash equilibrium? And so recent joint work with Yakov Bichenko, available in archive, we prove, okay, so two-player, again, they each have an n by n matrix, so obviously in polynomial in n communication, they can communicate their entire payoff matrix, and then they can find Nash equilibrium offline. Well, we proved that for epsilon Nash, this is indeed necessary. You need polynomial in n. And then in n-player game, you actually need 2 to the omega n communication. Wow, 5 minutes, I'm done. I thought it would be overtime. Okay. No, I really am done. I really thought that would be overtime. So, yeah, main theorem. Epsilon Nash requires quasi-polynomial time. Again, this is there are really unusual use of the PCP theorem, and there's this awesome open question about PCP for PPAD. Thank you. There's lots of time for questions.
Questions?
Oh, yeah, sorry. So I stated, so the question was, okay, I won't repeat the question, I'll explain the answer. So I stated, okay, so the question, oh, sorry. The question was, ETH, I assume that n of a line actually takes 2 to the omega n. What if it takes slightly less time? Actually, I never even write 2 to the omega in the paper, I write 2 to the omega tilde, and even if to get super polynomial lower bound, you just need 2 to the n to the 0.51, or even slightly less. So the reduction is approximately size 2 to the root n, so anything, if it takes any longer than that, then you go super polynomial. Run. Thanks. So the question is, are there any other applications for PCP for PPAD? So the answer is yes. In the paper, we give two corollaries, two immediate corollaries that would follow from PCP for PPAD. One is for a multiplicative variant of approximate Nash. Another is for this amazing problem of allocating courses to students. And again, you get much stronger hardness from if you assume this PCP for PPAD. And I'm sure there are more. For any other PPAD hard problem, many of them you can get stronger hardness, qualitatively stronger hardness if you assume this PCP for PPAD. Does the lower bound say anything about the dependence on epsilon? So the lower bound works for some constant epsilon. It's a very small constant. Yeah, that's all I have to say. And there is some open range between that and the 0.33.
Any more questions? Okay, let's thank Aviad again.